All right, today we are going to,
Starting memories.
Make him giggle.
I'm gonna move, we're actually gonna skip over 5.5 right now
Is this in the same type
to
of
be
structures?
determined whether we come back to that or not.
Is this in the same type of content as what we just
Sort
did?
of. Today we're gonna be looking at something called related
Or-
rates. Related rates.
Tongue twisters.
Not
Apparition. Epic ancestry.
And we have some strategies
Strategization.
that we're going to employ for these as well. And I'm sorry I don't have a nice little handout for you for this time.
Are you coming to the game Friday?
I don't know just yet.
Come on.
They better not take us out of school, because I don't learn when I'm at home. It's a whole lot easier when you're in class.
Very.
We'll have to do the best we can with what we got.
He usually does good. Usually.
First, you want to identify the variable. I guess I should preface it with this. When we're talking about related rates, before I even get into this first strategy here, we're talking about related rates. We're talking about two rates of changes that are going to be related to one another.
Yes.
If I have a balloon, and let's pretend the balloon is a perfect sphere. Of course, we know that most of the time those are not, okay? But let's pretend for a moment that it is. If it's a perfect sphere, and I let air out of it, okay, and not like release it and let it go, all over the room.
Yeah.
I just let it out. I'm holding on to it and I'm letting a little bit out at a time. The rate that the volume of that sphere, obviously the volume of that sphere is going to go down. The rate that that volume is changing by, that rate of change, is going to be related to the rate, in some way it'll be related to the rate that the radius of that sphere is also changing, because it's also going to be going down. Those rates are going to be related to one another. That's kind of the idea here, is we've got two variables that are related to one another, and their rates of change are going to be related to one another. So the first thing we want to do is identify the variable whose rate of change we want. You want to identify the rate of change, the variable whose rate of change we want. Next, you want to identify the variable whose rate of change we know. We're going to know one of the rate of changes. Okay, perhaps I know I'm releasing air in this controlled environment, and I know I'm releasing air so much, I'm releasing the volume, I'm decreasing the volume of that sphere by so much, like, I don't know, -1 cubic centimeter per second. Okay, that's going to be a rate of change I know. These are going to be rates of change over time. Okay, things changing over time. These word problems, you can sometimes get them confused with optimization problems, but the difference is we're talking about changing something over time, something changing. That's when it's going to cue you to a related rates problem. Some of the same strategies apply here, though. Draw a picture. We still need pictures.
You become an artist.
Okay. Label important parts from the problem. So if I'm talking about if I'm asking about a radius, how much is the radius changing by? Then we want to draw our sphere And we want to draw the radius. We want to put the radius in there somewhere in the problem, in our picture. Write an equation that relates the variables in number 1 and number 2, meaning the variables I'm referencing from the strategy 1 and strategy 2. Write an equation that relates those variables. The rate of change, whose rate of change we know and the rate of change we want. Write an equation that relates those variables though. If we're talking about volume and radius, I need an equation that relates volume and radius. These are usually geometric in nature, or otherwise they're given to you. Not always are they geometric, sometimes they're scientific, and they'll be given to you. You'll do a problem today with Ohm's law, for instance, with electricity. But the formula will be given to you.
How many strategies are there? Because I'm running out of room.
I'm sorry, 7.
Okay.
Differentiate both sides of the equation implicitly. Have we seen that word before? Implicit.
Yes.
Implicitly with respect to time, t. We're going to talk about things changing over time.
Six. That brother is six.
This next one's kind of the most, it's kind of really important. I'm going to star it. Because when people mess these up, this is the number one misplaced that they'll mess it up if they're not careful. These are kind of more or less not really strategies, but steps actually, maybe. Would have been a better label really for these, I guess. After differentiation and only after, I'm not going to write only after, but I'm saying it. After differentiation, substitute values in that change over time. I sometimes will call these your non-frozen quantities. Certain things in a problem won't change. Okay? You may get to change those. You may get to substitute those in, you may get to substitute those in before differentiation. But anything that changes over time, you cannot substitute that in. So maybe I want to know, hey, at what rate is the radius changing? If I'm releasing air, and air is being from this balloon, and so my volume is decreasing by, or my volume is changing by a negative, it'd be a negative rate of change because it's decreasing. My volume is changing by negative 1 cubic centimeter per second. when the radius is 5 centimeters, how much is my radius changing by? Obviously, the radius is going to change over time, right? It's not going to be 5 centimeters the whole time because I'm decreasing the volume, right? That 5 centimeters for the radius cannot be plugged in until after differentiation. I have to differentiate. I have to do number 5 first before I can plug in things that are not going to change over time. But if in a different problem, let's say that we want to take let's say that we want to take and we want to change the voltage of some sort of, we want to take the voltage equals the current times the resistance. That's Ohm's law. And we want to change the voltage, but we want to keep the resistance the same. We want to find how much the current is changing by. Okay, well, the resistance, since that doesn't change, we can plug that in prior to differentiation then, in that instance. But we won't always be able to do that. There may be multiple variables, and there may be multiple rates of changes that we actually do know. We may know more than one rate of change, because the formula may depend on more than one variable. Okay? Finally, interpret the solution in context. Just like with optimization, you must interpret your solution in context. If this is a free response question, which they will sometimes be, you have to write the answer in terms of the context. All right, let's look at an example.
How big of an example is this?
He backed it up.
There's a little bit of words to it, but
Big.
we'll have to draw a picture too. A
I
hot air
think the
balloon.
example would be really hard.
A hot air balloon rising straight up from a level field is tracked by a rangefinder. Have you ever heard of a rangefinder?
No.
What?
No.
No? Nobody heard of a rangefinder?
Someone to find your range.
It's like an object it'll just measure how far away an object is, especially if it's like moving.
Not that big.
If I had enough money, I'd buy one of those fancy ones that you can attach to these calculators, and like you can collect data from them.
Like,
You could be able to collect how far away something is. Then I could, figure out the speed by doing the derivative.
Oh, I thought you meant like how much a student uses it.
No.
They make
How
it-
much
Huge.
are
3
one of
days
those?
of it.
My calculator said earlier in the day it needs new batteries.
Yeah, mine
my
does.
calculator needs to program for the quadratic formula.
By a rangefinder, I'm sorry, 500 feet. You won't need a quadratic formula for this. 500 feet from liftoff point maybe I should say the liftoff point. at the moment, the rangefinder's elevation angle,
Oh, angle of elevation.
Yes.
so you know where this is going. This is gonna include,
Trigonometry.
Joy.
Why do you get such a rise out of this?
Because he likes trig.
Because he likes torture.
Is trig your favorite?
Yes. How do you not figure that out?
I really love teaching calculus.
I don't like
He
learning
just
it.
loves those little sine, cosine, tangent.
Pi over 4
IOUOUI.
If I
Your
understood
elevation
what
angle
they were, I wouldn't like it.
is pi over 4 radians. The angle is increasing at a rate of 0.14 radians per minute.
How far is it?
How fast is the balloon rising at that moment?
I swear on the ACT we give all that and ask you something completely random.
How hot is this?
So let's find the rate of change we want. What is it asking us to find?
Velocity.
Well, it is sort of a velocity, but how fast is the balloon rising at the moment? So we're talking about a rate. Sure, it's the speed of the velocity of the balloon,
Except
sure.
The E word, wasn't it? The
What?
I word? Or asking what kind of rate is it? Like the,
We
if you're asking
want.
for it at the moment, then you're asking like the, I can't remember the word for it.
Well, it's rising at 0.14 radians a minute, right?
That's the angle. We know, so we know that the angle, look, we know, sometimes it may be easier to first do what we know. We know that the angle is increasing. We can call our angle theta. Angle is changing over time by 0.14 radians per minute. So d theta dt, we know d theta dt, the angle, I called it theta for reference, but whatever angle you want to use there. That's equal to 0.14 radians per minute. If I'm talking about how fast the balloon is rising at the moment, I'm talking about how high the balloon is. So I'm really talking about a height, sort of. It is a velocity though. You're not wrong. But I'm going to be looking for dH/dt. I need a formula that relates this. So I need to draw a picture for sure to make sense of this problem. So we've got to draw our balloon.
Let's see it. Yeah.
Beautiful.
Okay.
Doing it exactly how you would.
We had the liftoff point. It lifted off from a level field. We've got this rangefinder somewhere over here that's measuring how far away it is. And the angle that this rangefinder is measuring right now, we know that that the angle right here, theta, we know that theta is changing by 0.14 radians per minute. At that moment, though, it's pi over 4, but of course it's going to change. So here's our height. There's something else that we know.
The 500 foot.
Yeah, is that changing?
No,
Yeah, it's because it's rising up.
no, the rangefinder's 5 feet away
500
from
feet from the liftoff point.
Stay. It's gonna
Oh, so
stay.
the-
This
That means-
rangefinder is 500 feet from the liftoff point. It doesn't tell me that I'm moving around with the rangefinder.
So that means it's,
staying.
That's staying the same. That means that's frozen. That's frozen. That's staying the same. That is not changing over time. That means I can plug that in prior to differentiation
we just,
because that's not changing.
can we just bag it up?
Well, no, because I need a formula that relates theta to those two sides.
Well,
Well, you got the.
Which one?
You have the.
Which one is SOHCAHTOA?
is it opposite over
Adjacent.
adjacent?
10.
So it's going to be a tangent. Tangent of theta, for our equation, tangent theta is equal to the opposite side h divided by
Adjacent.
the adjacent side 500.
So whatever the height of a balloon is. Okay.
Oh, Lord.
Let's solve this for h because we want dh dt. So why not go ahead and get the formula in terms of get h by itself? Because we're going to eventually want dh dt.
So we should just multiply.
So we multiply by 500. And we get 500 times the tangent of theta. Is equal to h.
And that's your.
That's my
your original
equation.
height.
That's my equation. But now we're ready to take, and we're ready to differentiate both sides implicitly. We're differentiating with respect to time though. So every time we differentiate a different variable, we have to attach a d whatever that variable dt. Just like when we had differentiated y with respect to x, we had to attach a dy dx to every one of those terms, remember? When we did implicit differentiation. Remember when we differentiated like xy, the mixed terms were always a pain because you had to use the product rule? There'll be times where you have to use the product rule here too. Not in this one, but you will have to sometimes. All right. So I'm going to differentiate both sides with respect to time. So 500 tangent theta with respect to time. Differentiate h with respect to time, I just get dh dt. Well, the derivative of h is 1, right? Derivative of just a variable like that, h would be 1, but it would be 1 dh dt. 500 is a constant multiple. So I'm just going to take 500 times. What's the derivative of tangent?
Cosecant squared.
Nope.
Derivative.
Nope.
No, it's not cosecant. It's
Secant.
sec. It's
I'm going to
sec
revoke
squared.
your driver's
I knew
license
it's
and make you
squared.
take the test
I knew
again.
it.
Squared.
I knew it was- I knew it
Secant
was-
squared.
I just said, I knew it was sec. I just said in my brain, I knew a sec.
But we have to attach a d theta dt when we do that. Because we're differentiating implicitly.
You should get rid of 500, shouldn't you?
No, because it's a constant multiple. It's not 500 plus tangent.
Okay.
If it was a term by itself, yes. But it's not. Do we know d theta dt?
Yeah.
We do. It's 0.14, right? Do we know theta at that instant? Now that we've differentiated, now we can plug in things that change over time. This is what I'm talking about, number 6. After differentiation, now you can plug in things that change over time. So we know that theta changes over time, but what is theta at this instant?
Pi over 4.
Pi over 4. So we're going to take 500 times secant squared of pi over 4 times 0.14. That's our dH dt. And we can actually do this. Secant of pi over 4, well, pi over 4 is 45 degrees. I don't think good in terms of secant, but on the unit circle, I'm really good at finding sine and cosine because sine is the what
Y.
coordinate? The y, and cosine is the
X.
x. But secant is the reciprocal of what? Sine or
Cosine.
cosine? It's the reciprocal of cosine. So I'm going to flip the x.
So we 1 over.
I'm going to get 2 over radical 2. The x coordinate there is radical 2 over 2. So when I flip that, I get 2 over radical 2. I'm going to square that. So I have 500 times 2 over radical 2 quantity squared times 0.14. This actually comes out nice. It comes out to be 140. Because what you get is,
You get 1,000.
yeah, because this will come out to be 4 over 2, which is 2.
Squared is
When you
4.
square it. No, I've already squared it. When I square it, I get 4 over 2, which
Oh,
Yeah,
is
so you
2.
just come out with 2.
2 times 500 is 1,000, and 1,000 times 0.14 is 140.
Yeah.
So you get 140. That's dH dt.
So that's the rate it's changing.
And what is that rate? Let's get this in context.
That's the rate the balloon, that's how fast the balloon is rising. The rate of its speed.
At this moment, the balloon is rising 140. What are the units on that?
Radian?
Radians per minute.
Nope,
You would have feet.
feet per minute because it's a distance. It's rising at 140 feet per minute.
Mine up per second.
That's going up pretty fast. 140 feet per minute?
Yeah.
Never mind, I figured.
I mean, it's pretty fast, isn't it?
How fast?
I mean, that is
Not
pretty
terribly,
fast.
maybe.
I mean, that's like half a football field.
It's
Yeah.
2 feet a second. 2.3 feet a second.
No, I don't think that's not fast.
Okay, well,
But
Faster than you could run, Tad.
probably.
Yeah.
Do you think you can run 2.3 feet a second?
straight up.
Straight up.
2 feet a second. Let's see.
You probably could do 2 feet in a second, I'm sure.
Yeah. That's like a 8-second 40
Luke,
yard
you
dash.
could roll 2 feet. in a second. So you could do it.
2
All right.
feet a second.
Not too bad, right?
Yeah.
Man.
Yeah.
Now give us the hard one.
Yeah.
I give you 20 seconds. See if you can run a 40 in 3 seconds. Wait, I think I did it. I don't know.
20 seconds.
Yeah, I think. I don't know.
I couldn't do that because they'd spend 2 hours taking me to the hospital. Why? I'd rather run 40. I'd die.
Why?
Because I can't. I'm not good at it.